So welcome guys, welcome to this introduction to computer vision. In this conference, we'll go before. Okay. In this conference, we'll go over some basic steps to building your own model. We'll also see some different categories of computer vision models. So I'll begin with a quick introduction of myself and what I do. So I'm Tom Joris. I'm currently studying EPITA in the second year of the engineering cycle. Faut que je parle vraiment fort? Ok, nickel. Vers le micro. Genre, je le prends comme ça. Non, attends, ok. Ok. Est-ce que c'est bon là si je parle? Je pense pas. Bon. Sinon, je le mets là, comme ça. Si je parle comme ça va? Genre devant le micro là. Ici. Ok, nickel. I'm in the computer vision major, SCA major, which has the specialty computer vision. Our major is the EPITA's major on AI and data science, and focuses on analysis and optimization math. Also, we review a lot of deep learning models, deep learning articles, etc. We go from the basics of AI, fundamentals of AI, whether it is mathematics, to building our own models, and we also review state-of-the-art models. We also do some big data engineering. So this presentation basically is in 4 steps. First step is a quick intro, just to quick refresh on machine learning for some, and quick machine learning intro for others. And we'll review some machine learning concepts, key concepts that you'll need for the rest of the conference. And then we'll see the different categories of computer vision, its applications, and the most known models. And then we'll see what's the workshop about. So the workshop will be available right at the end of the conference. And at last, we'll see the contest. Will be available at the in the next week, I guess. So here are the different links you need. So if you want to participate in a competition, I suggest you going on the Discord server. You will have access to the slides, so don't worry. So let's start with a quick intro to machine learning, and we'll go over some. So we'll first start with what is AI? So that's the question, right? AI is a quite broad term. It has a lot of meanings. Basically, AI is when a machine or an object tries to mimic the human behavior, sorry. So that would be a robot, basically, or a computer or machine. So a lot of the time, people mixes machine learning with AI. Machine learning is AI, but AI is not necessarily machine learning. For example, a bot video game basically has been hard-coded to mimic a player's gameplay. This is AI, but this is not machine learning, as we will see just in the next slide. Another type of AI would be a robot, so an automatic vacuum cleaner will simply go over a predicted path in a room that it will calculate by itself, but that's also not machine learning. So AI is basically every time it mimics a human. So basically, machine learning is more specific, as it's a definition of learning from data, which is not possible in a standard AI, I would say. Machine learning will adapt its behavior according to the data, and no human interaction is really needed for the AI to perform, for the machine learning algorithm to perform. For instance, an AI, a simple AI that is not machine learning, would be hard-coded by a human. There are 3 different categories of machine learning. So the first one is supervised learning. This category of machine learning is works on data that has been labeled. That's how it's called, labeled. We put a name or a feature on each piece of data. For instance, here we see some squares and circles. Each label would be whether it's a rectangle, circle, triangle, hexagon, etc. So the AI needs labels to perform its supervised learning. An example of a type of algorithm would be the on top of datasets, of data, would be the digit numbers written by hand. So these are pictures of the different digits, and it's labeled. Well, the different labels would be the number associated with the hand-drawn digits, and then the network has to give us the label back. So basically, we give it the data. It needs to predict its label. The next category is this unsupervised learning. This is simply just unlabeled data. We have no information about it. We just give the network the data and it tries to find patterns and tries to classify them or regroup them, cluster them. It really depends on the data and the type of algorithm you're trying to work with. So this one is a lot more unpredictable than the supervised learning, but it's used to find patterns in data. The last one is reinforcement learning. This one is actually more the most common reinforcement learning techniques are like a video game, basically. You spawn a batch or a group of agents which live inside an environment. This environment will challenge the agents, and the agents' goals are to get as much rewards as possible. So, for instance, on this video, you can see that's a car simulation. We try to help the car drive along the path. So we feed each car 5 sensors that are on the car, and this data, which are the sensors according to the distances between the walls, etc., are fed into the network, and it tries to process this information and gives an output of steering and moving forward, basically acceleration. And the best agents at the current generation are copied, basically, and moved on to the next generation. And as the algorithm keeps going, the best cars, we get a car that can really drive along all the paths. So, for example, at the end. That's an example of reinforcement learning, but there are other ways of implementing it. So another category, which is not really a category of machine learning, but that's more like a category inside machine learning. That's deep learning. So basically, machine learning, the old way of doing it was we had data which a human needed to label specifically on complex things. Like for example, in an image, a human were to label, I don't know, glasses on someone, mustache, or its skin color, whether it's bald, has hair, etc. Or in a car, it would say it has tires on the picture, etc. And where are the tires on the picture? But with deep learning, you just give it the picture, and it by itself will extract the features in the image. That's what's powerful about deep learning. You don't need a human to label each piece of data to extract the features in, for instance, an image, but that could be on anything. And the deep learning, as we can see on the second graph, which is really crude, but the deep learning can really perform better than standard machine learning on the amount of data that's given. more data you give it, the more features it can extract, and so on until the network performs better than the older ones. At this part of the presentation, we'll go over some basic concepts of machine learning. First one being the data sets, because the algorithm need data to function. So we need an object to feed them with, and this object is called a data set. So for example, we have all the data, and we'll split them into 3 categories. This way, by splitting the data into 3 categories, we can evaluate the training of the model. So the training part of the data will be used to adjust the weight of the model, for instance, or perform a gradient descent, as we will see later on. And the validation at each iteration of learning will validate if the model is going in the right direction, basically, if it's learning the right thing. And the test one is when the model has fully learned on every single piece of data. You want to test it on a real example. So validation and test is not the same thing. Validation is each learning step, and the test is at the end when the model has finished learning. And the second concept is the batching. So this one is a bit maybe a bit specific, but batching would be just slicing the data into a small piece of data. This is just a common practice to lower the memory costs. So another very important concept in machine learning, more in deep learning. This concept, so the convolution, is a mathematical operation you apply on one matrix regarding the kernel matrix. So you get the input matrix, and you apply the kernel matrix on each piece of value in the input matrix. So it's like a sliding window, I would say. So yeah, on this video, you can see that the model, that the kernel is applied on each coefficient, each value, according to the kernel's value, and we sum the different multiplications with the kernel in the output matrix. Usually, this reduces the size of the input matrix and the input matrix, sorry. So we try to add, that's called padding, that's adding data to have the same input size as the output size, because in real life, you want to have the same image size as the output size, for instance, on an image. So when you add, basically pad values around the matrix, because the kernel matrix reduces the size of the output matrix. The steps, each iteration is called strides. That's the steps the kernel takes in every direction. So, for instance, on these GIFs, it's step 1. The kernel size is also a parameter. The convolution are very strong at identifying certain features in an image. This is why we use them on image data. We can see different kernels. Each kernel has its own ability to identify things in an image. These are standards one, but if you, the key point here on deep learning is telling the network to find the values of the kernel by itself. So, for instance, you would use 17 convolutions in parallel, and for each of the 17th convolution, you will try to find a certain thing in the image by adjusting the kernel's values. For instance, if you were to put this kernel, so the edge detection kernels, you would have the edges of the image that would be very visible. It just takes the closest pixels to the center pixel, which is the one that's being used. and it's so that gives us the edge detection system. The model will learn the different values of the kernel. We'll see that later on. Another concept is pooling. So in larger models, you would have enormous size of matrices. So we try to use pooling to reduce them and also reduce the number of parameters in the system, in the model. So that gives us an advantage because we have to, that reduces a term that's called overfitting. We'll see that later, but pooling is a good practice. So neural networks, that's the type of model we'll use in the workshop. This type of model is actually a simple mathematical operation that's read from left to right. The neurons, which are the dots in the model, are interconnected from one another, but are only connected from the left to right. So for instance, if you take the violet, the purple neuron here, to calculate its value, each time you want to calculate a neuron's value, you will use the connected neurons values as well. And each connection between neurons has its weights. And these weights will be used in the calculation. So that's just a sum between the neuron, the weights, and etc. And it gives us the value of the neuron. But that's just the problem with using only this explanation is that if you only add numbers and multiply them, you can only solve linear problems. And that's a problem because a lot of the time the data uses nonlinear problems. So to overcome this, you will use activation function. So once you've calculated the value of the neuron, you will pass it in the activation functions, which will either clamp the value between 0 and 1 or -1, 1, etc., or simply reduce and break the linearity of the model. And once you've done that, so from left to right, you calculate each neuron's value. That's called forward propagation. You get a prediction from the model, which is just reading the last values of the last row, the values of the neuron of the last row. That's called a prediction, and you compare it to the real values, the ground truth values. Yeah, that's supervised learning. Neural networks are mostly used in supervised learning. So to compare them from the real values, you will use a loss function. This loss function helps you find at how much the model is wrong, basically. And that gives you a loss score, which you will use not just like that. You will use them in an optimizer. This optimizer will use the loss as an indication on each weight of the model, each link. It tells us, yeah, you need to change this weight a bit less or a bit higher. And this is how it learns, basically, by calculating the loss difference it needs to apply on each weight. And that's called backward propagation. So that's a cycle you repeat. Each time you repeat it, you need to test if it's better on the validation dataset that I've talked about earlier. So what is the loss function, basically? If you were to use a binary classification, for instance, you want to predict if it's whether it's 0 or 1, it's just binary. You would use a cross entropy loss. It just basically measures how you were wrong. If it's 0, that's a loss of 1, approximately. And if you predicted 0 instead of 1, that's 1 loss. If you predicted 1 instead of 0, that's 1 loss, etc. That's of course that's more complicated, but that's basically how it works. And the multi-class classification is the same, but for an infinite or finite number of different possibilities. And the regression would be on a continuous model with continuous values. For example, if you were to predict a car's model, if you were to predict a car's price based on its fuel consumption, for example, that would be the continuous value. So that's the different loss functions. And the choice of loss function is actually very important in the training. So this loss function, if you were to represent it in 3D space for a 2D problem, for example, two possibilities, that would look like that. And if you understood correctly, the loss function, we're trying to minimize it. The lower the loss function is, the better the model is. And this is why our little dots here, which are the different algorithms, different optimizers, as I've talked earlier, they will try to find the lowest global minimum, the global minimum. So for each weight, we'll try to find the lowest point in the graph for each weight, according to each weight in the model. And there are many algorithms to try to find the lowest minimum. And your choice of algorithm is actually depending on the problem and the data you feed in. So if you were to put too much parameters in your model, for instance, you put, I don't know, 2 million neurons, simple problem, you would go on something that's called overfitting. Your data, which always has noise, so kind of things you don't want in your data, but that's there anyway, so you want to ignore it, basically. And overfitting will fit the noise. That's a problem, because the noise is random, and your model can't predict randomness. So that's just saying you're wrong all the time. And what you want is optimal fitting. So you will find that which part of the data is noise and ignore it. And underfitting, of course, is when you don't have enough parameters to adjust the data. That's for three different categories, but that's basically the same thing each time. So the loss function is great for the model to learn and understand where it's wrong, but for a human, that's not really, that's hard to understand. So we use metrics to really define, as a human, really comprehend how the model is working with our data. So most of the time we use accuracy. For instance, on a binary classification, if you had an accuracy of 50%, that would mean you were just random. So we are trying to find the best accuracy, so near 100%. Sometimes you don't use accuracy. For instance, if you want to detect cancer cells on someone using, I don't know, an image of an X-ray of them, you would prefer false positives than false negatives. Because if you have a false negative on someone, that would probably kill them. So you prefer double checking than being wrong negative. So this is why the choice of metric is important. To avoid overfitting, there are many ways to do that, but one common way is augmenting the data. Using data that's already existing, you will apply data augmentation, which will artificially enhance the number of different possibilities in your dataset. So the model will generalize better, and so your accuracy or your metric will be better. So once the model is trained, that's something really important. When the model is trained, basically you don't have to retraining it again to get a prediction from it. So you just have to, once the model is trained, you can just pass it an input, and it will give it an output. You don't have to train the model again. So this is why on your phone you can have a trained model very easily, but you maybe could not train a model on your phone. So that's like a computer program, basically. Once it's compiled, you can run it easily. So an important concept in deep learning, basically, the transfer learning. Most of the time, you don't have the computation. You don't have the computation or the resources to train your enormous model. So you will use an already trained model from Google or so, and use it in your project on your data. Even if the data is maybe different from what they've trained on, that's not really important. It needs to be similar, but the similarity is sufficient. For instance, most of the time, the images the models have been trained on is a big dataset ImageNet. That's more than 1 million images with 1,000 different classes, so different things. And using this model is actually very beneficial because instead of starting on random weights, you start on weights that have already been trained, and this speeds up the process. You can adapt basically the knowledge the model had to your problem, and this speeds up the process. You just happen at the end your classifier, and you can choose to unfreeze certain weights that have been trained to fine-tune it. We'll see that in the workshop. So another key concept, I think it's the last one. Last one is normalization. This concept is simply a good practice. You don't have to use it, but that's just better. In general, the model, the algorithm, the optimizer will converge better to the optimal solution if you normalize your data. Okay, so once I've talked about the different concepts, I can talk about what is computer vision basically. So I'll start with that's computer vision. So I'll start with some history of computer vision. So in 1963, Larry Roberts, who is basically the father of computer vision, described the process of taking a 2D picture and getting a 3D model. I won't go over every single of them, but you can see the progress is really accelerating the years passing by. For instance, in 2012, you couldn't classify images as cats or not cats, and literally 5 years later, you have facial recognition. So that's something really nice. And between 2001 and 2017, 2001 was not using neural networks. It was AI, but not machine learning. So that's why there's a difference between 2001 and 2017. And also, you could use it on your phone. So that's something that models have reduced in size. So the different categories of computer vision are the segmentation, detection, classification. So I will start with classification. So classification has 3 types. First type would be binary classification, whether this image contains dog or not a dog, or is not a dog. Cannot tell you if there are 2 dogs or maybe dog and a cat. It cannot differentiate the numbers of dogs. It can just tell you this image contains a dog. In multi-class classification, it can tell you on multiple classes, but that's just the same thing. If there are a dog and a plant, it doesn't know if it's the dog or a plant. That's basically or each time. And in multi-label classification, that's where it can detect every single class on its own. So dog and a plant. An example of classification would be the handwritten digits. So that's feminist. It's called feminist. For this kind of data, you would use this kind of model. So this one, which is applying in convolution several times, followed by a pooling, and at the end, flatten. So flatten is just taking a matrix in a 2D space or n space, and flattening it to a simple column. Sorry. And at the end, you would have the n-way softmax. The n-way softmax is just 10 neurons in this case, that would tell you if it's a 0 or a 9, 2, 9. These models use convolution to extract features from the image. This is very powerful in classification, the convolutions. As you can see, the further you go into the convolutions, the more detailed are the extracted features. So if you check what's inside the convolution, you will see this kind of images. That's called the features extraction. So an example of loss you could use, as we talked earlier, is the cross entropy. So you could upgrade your model by using localization. Localization is based. I love this image. Localization is basically just finding a bounding box that fits an object on an image. If you think about it, that's just 4 parameters you need to find on the image. 4 continuous parameters you need to find on the image. An example of data would be taking the different digits in the data here and expanding the image and putting the digits randomly on the image and trying to find the corresponding bounding box. An example of model using this is you can use the exact same model as before, but adding a second output layer, which would be the bounding box regression layer. Regression is finding a continuous value instead of just discrete values like 0, 1, 2, etc. An example of loss for localization is IUU. IUU, yeah. That's just the intersection divided by the union of the truth value and the predicted value. So in this case, bounding box. So another concept, which is more advanced, I would say, is object detection. So the object detection models can localize objects on a scene, multiple of them, and classify them. This process needs to apply that's not the newest process, but the old processes were working like that. So that's a sliding window. We'll try to classify each bit of the image at different resolutions. And each time it is confident on a certain class, we'll keep them as a group of different bounding boxes, and then it will just get the most accurate, the one that's the most confident. So there are 2 main models on this kind of detection, which is YOLO and SSD. The YOLO model is actually very fast compared to SSD because it will apply this classification model, which is the slowest, part of the model. We'll apply them to only the best found, the best extracted features. This is why it's really it's faster than SSD, which will apply a classification even if we don't have any features extracted from the image. Okay, so now the segmentation part. Segmentation will tell you each pixel on the image, which class it is, which class it is part of. The segmentation always is the same. That's an encoder, which we use which gives us a downsampled feature map, and then we put it into a decoder, which gives us the final image defining classification of each pixel on the image. There are 2 types of segmentation. The first one is the semantic, which will just tell you whether this pixel belongs to a class or not, but it cannot distinguish between 2 entities, basically, of the class. For instance, the persons there are different from one another, but the model cannot distinguish them. Whereas in instance segmentation, it can separate them pixel to pixel. Okay, so an example of a semantic segmentation model would be a UNet. This one is very straightforward. First half of the U is the encoder, and the second half is the decoder. This model will, at each step, apply 2 convolutions. So the first one will extract the features, and the second one will try to find the best features extracted, and then we apply deconvolution, which is the inverse operation of convolution. So we try to rebuild the previous image before applying the convolution. And we do that for every single step. This gives us a small image, basically, of 138 flat array. And we use that as a to the decoder, which will give us an image classified pixel by pixel. I won't go into the details there, but you can always check the paper. An example of an instance segmentation would be the mask RNN. This is very slow. That's why it's not very used anymore. So this model will extract the features using the convolution layers, and then on each of the best features extracted, we'll apply at each spatial location, as it said, its classifier, which has also an extractor of features, and only then it will apply for each ROI algorithm. And then we get the image classified pixel by pixel and instance by instance. We can do that because we apply the algorithm for each different instance, which we don't do. Do in the previous model unit. So an example of a segmentation loss would be the IOU doesn't fit on this one because the IOU doesn't really punish you if you're not predicting correctly. The dice coefficient is better on this part. So okay, so now that I've explained to you what are the different categories of computer vision, I'll go over the available workshop you can use to learn and practice on TensorFlow on building your own deep learning model, which will be on classification. So we'll use TensorFlow, which is the Python library. You can use other languages, of course, but Python is the easiest, I would say. This library is the most common for building deep learning networks. So let's view a quick example of the code, of a TensorFlow code. So the first step would be importing the different libraries. TensorFlow is built on top of Keras. So it overlaps Keras, basically, overrides it. This is why we're using TensorFlow.keras. Once we've imported the different libraries, we can use the built-in load data. So Keras has its own data set in the library you can import easily. So we import them as arrays of data. So the data works like that. You have a 2D array, and each coefficient is whether the pixel is grayer or not, or darker. Once you've done that, you need to convert them to TensorFlow dataset, so you can apply easier functions you need, and also it's faster. So using the TensorFlow datasets, you can apply a function very easily and fast. This function is normalizing the data. So we talked earlier, instead of values between 0 to 255 as an integer, we'll divide them by 255, so we get a continuous value between 0 and 1. Once we've done that, we split the data into 3 parts with a 20% validation size. Then we batch them to optimize memory in bits of 32 by 32. And then we'll build the model. So building a model in TensorFlow can be very easy, like that. You basically just stack them. So flatten will take the input image as a 28 by 28 array, and then you flat it into a 784 one-dimensional array, and you put dense layers. Dense layers are the interconnected neural network, as we've talked about earlier. So I did not represent the different neurons. There are just too many of them and too many connections between them. But each neuron here is connected. And then you apply the last layer, which will be the classifier. It would tell you with confidence, that's a probability between 0 and 1, whether it's a 1 or 2 or etc. And each time we need to apply an activation function to better fit the data and break linearity of the model. And lastly, we'll compile the model using the optimizer. So compiling is not training, that's just saying the model is built. You can use it as so for the training. So we'll use Adam, which is the most common optimizer. And the loss is the cross entropy we've talked earlier. Don't mind the sparse. And in the next part, we fit the model. So that's the backward propagation, forward propagation we've talked earlier. It will do that 5 times on the whole data set. That's what an epoch is. And once the model is built, we can test it. Once it's trained, sorry, we can test it on the test data set. You will see this piece of code in the workshop. So the workshop goes over the CIFAR dataset. That's 10 class you need to classify, 10 different classes. The images are very different from one another. So this is why this problem is very interesting. You need to find a way to, the model will find a way to remove the background on each image. So this is a classification problem. And in the workshop, I really emphasized in improving the model each time, relatively. So each time you find that the model is not very effective, so you add different layers, you change the data, you change the parameters to better improve the model. So this is the different parts of the workshop. I did not put it there, but the workshop is split into 2 parts. The first part is the easiest. It's just the deep learning basics in TensorFlow. You will build the model at the end. You will go over to the convolutional neural network in the first part. And in the second part, which is more advanced, but still accessible, you will use the data augmentation to improve your data and further improve your model and reduce overfitting. And then you apply dropout, etc. I'll explain everything in the workshop, sorry. And lastly, maybe once you've learned from the workshop, you would like to practice on something that's not a real life problem in this case, because that's a video game, but you would like to practice on something that's challenging. This is why I suggest you to participate in the Kaggle contest. Yeah, so Kaggle is the Google's platform for the data science competitions, the contest. This rates your model using a metric. Most of the time it's accuracy. And you need to have the best accuracy in the leaderboards, just like a video game basically. And you build your model on Kaggle, and it will sort you in the leaderboards. So the given data on the contest is the screenshots of the video game Minecraft, and each screenshot is not inside a building or something. That's just a screenshot of the vanilla game in every single biome. You need to classify each screenshot as which biome it is. For instance, this one is purely a forest biome, dark oak, I think, for a biome. You have plains, snows, desert, etc. The data set is quite complex, but I'll let you tackle with it and try to find what's the best strategies to classify it. So the rules are not fixed yet. The competition, the contest is not ready yet, but it will be on the 22 June, 22nd June, so in 1 week. And it will last, I said 5 weeks, maybe that's too much, but I think it's minimum is 3 weeks. So yeah, you will have 3 weeks to improve your model and basically be the best. classifying the biomes. I will provide you a skeleton, so an empty script. So you don't have to bother importing the data, etc. You will just have to build a model. Yeah, the rules are not fixed, so I won't read them. And we'll also have some prices for the best of you. So the 10 best will have prizes, and the third best will have bigger prizes. Okay, so here are some quick tips on the contest. So you will see that in the workshop, but using successive convolutions and poolings is really the key here. That's because that's the architecture of VGG. You can take a look at this model to have an idea of how to build a model, what model works the best. And don't forget that the validation data is what you're aiming for. The accuracy on the validation data or the loss. And the data is very unbalanced, which means a class, many classes have more images than others. For instance, I think the desert biome doesn't have many images. So you need to find a way to balance the data so your model doesn't just forget 10 biomes and classify them as something I don't need. And don't overfit, because if you overfit in the leaderboards, you won't go very high. Since the leaderboards we use the test dataset, you don't have access to. And this will be in the skeleton, but don't forget that at the end, your Kaggle script or Kaggle notebook should output a submission file in a CSV format. This will be in the skeleton, but just don't delete the piece of code that does that. And of course, inspire yourself from the workshop. And also, don't hesitate to contact us in SCIA. We'll gladly help you and give you ideas on how to solve the problem, tackle the problem. Of course, maybe don't team up with someone of SCIA. You can, of course, but some prices can be split in half. So if you guys win at the same time, we can split the price in half. You need to choose. Okay. I don't know if you notice, but in the first image, this image is actually 20% computer generated. So this is the real image, and the left image is DALL-E, second DALL-E. Okay, so thank you guys for listening to me. And if you have any questions on whether it is on the conference or on the workshop or the contest, you can ask me here, or you can find me on these different links. Okay. Any questions? Okay, thank you guys. Okay.